All right, well, welcome back. So in the previous lesson, we started to have a look at the series of real numbers. We also started to have a look at the convergence of a little bit of the convergence of the series of real numbers. So we had a look at the definition. We had a look at the sequence of partial sums. We also tried to have a look at particular examples, namely the geometric series, which is an important one. And we tried to use those to use the geometric series to see what series will converge or not. So we had a look at that. We also had a look at the telescopic series where it will simply just be equal to 1, the sum itself. And we also had a look at the harmonic series, which is a typical example where it will actually diverge. Okay, so uh, we have the theorem as well. So if a series is convergent, then the limit of the terms sequence of numbers is going to converge to 0. As well, we also had to look the contrapositive of that. So meaning that if the limit does not equal to 0 or does not exist, then the series diverges. So that was from last time. This time, we're going to have a look at some of the convergence tests for series of real numbers. So the first one that we're going to be having a look at is called the integral test. Okay, so first let us consider the series that is given by the sum of 1 over n squared. So there is no simple formula for the nth partial sum, but we can approximate it by putting into a calculator. So if we add all these terms up and keep on adding it forward, we would see that it would actually converge to some number. However, we can approximate the series uh, above by using a function that relates to an, where f of x, where x is a real variable that ranges from 1 to infinity. So in this case, what would the function be if we were to relate 1 divided by n squared to f of x? Well, here, if I say, well, let f of x, so I'm going to say let f of x be equal to 1 divided by x squared. Because if we substitute n instead of x here, so if I replace this by n, we get the terms of the series, 1 divided by n squared and 1 divided by n squared. So that means if we replace the n by x, we have the function f of x, 1 divided by x squared. All right. So let us try to use the graph and see if we are able to compare the two functions. If we were to consider the discrete values and if we were to consider the function itself. So on the x-axis, let us go up by about 2 per 1 unit. So we have 3 and 4. So 1, 2, 3, and 4. On the y-axis, I'm going to go up 4, and this is going to be 1/2. And another 4, this is going to be 1. So the function, we should be a little bit familiar with this, looks something like this. So we have the shape. 2 would be 1 divided by 4, so it'd be around here. 3 would be 1 divided by 9, or 1, so 1/4 would be about over here. So it would look something like this as the function itself. Something like this. However, now if we were to consider discrete values, so from 1 to 4, um, we would actually consider rectangles in this case. So here we would have one rectangle looking like this, or roughly like that. I'll try my best. So that's one rectangle. We have another rectangle over here. Maybe something over here. We have another rectangle and another rectangle over here. So this looks a little bit familiar to us. We'll mention that in a second. So this area over here, since each length here is going to be 1, the height is 1, this entire area is going to equal to 1. And then if we were to add more areas, that would eventually, if we have more terms to it, it would actually equal to the sum over here. Okay, so if we divide the interval between 1 to infinity, each subinterval being the length of 1, this should automatically be familiar because this is actually just going to be Riemann sums here. So this is Riemann sums. But this time, the interval that we are, or the interval that we are considering is going to be 1. So now, if we take the integral of the function from 1 to infinity, does the integral converge or diverge? All right, so let's try to compute this integral over here. Well, remembering that if we take the integral from 1 to infinity of 1 divided by x squared dx, this is just going to be equal to negative 1 divided by x evaluated from 1 to infinity, which would just equal to 1. So because the series here converges to 1, that also means that the series would also converge as well. So since the integral converges, so does the series. However, one thing to keep in mind is that it is not always the case that the integral here is equal to the sum by itself. That is actually not true at all. So that's one thing to keep in mind. And we will probably see why later on. All right. So let us move on. In general, we can use improper integrals of real functions to determine whether a series can converge or diverge. So this is the first test we're going to be talking about, which is called the integral test. So it says, let us consider a function f that is continuous, positive, and decreasing on 1 to infinity, and let an to be fn. Then the series is convergent if and only if the improper integral here convergent. So meaning that if this integral converges, then the series also converges. Or if this integral diverges, then this series will also diverge as well. All right. So let us have a look at an example. Let us determine whether the series converges or diverges using an integral. Well, so because we're going to let f of x here to be equal to 1 divided by x squared plus 1. And we're considering values for x being 1 to infinity. Then, if we compute the integral, so the integral from 1 to infinity of 1 divided by x squared plus 1 dx, this is equal to the arctan. So recall that this is the arctan of x, and we're evaluating from 1 to infinity. As it is approaching infinity, remembering that it's going to go towards pi over 2. So we have pi over 2 plus 1. Or hold on 1 second. Yeah. So that's going to go to pi over 2. And minus pi over 4, which is then equal to pi over 4. So since the integral converges, So does the series, which is given by this. All right, so let's have a look at another example. Now let us determine whether the series, this time starting from 5 to infinity, of 1 divided by n minus 4 to the power of 3 converges or diverges using an integral. Now, although we could start from 5, let us first adjust the boundaries so that we start at 1, just to make things a little bit easier. So we're going to adjust the boundaries. So adjust the boundaries so that we have an equivalent form. So this equivalent form is the same as saying 1 divided by n to the power 3. Why? Because if we're starting at 5, then that means we're going to have 1 divided by 5 minus 1 to the power 3, which is the same as saying if we are having starting at 1, if we put 1 in, oh, this should be 4 minus. And if we were, so this would be equal to 1. If we put 1 into here, we also get the same thing, same result. So that's why starting at 1 would be this form over here. So these two are actually the same. Now we compute the integral, which is given by 1 to infinity, 1 divided by x cubed dx, which turns out to be negative 1/2 x to the power negative 2, evaluated from 1 to infinity. And as a result, we only get 1/2. So because this integral converges, so therefore, since the integral converges, so does the series. Good. All right. So now, recall that back in examples 3.7.2, which is the example of the improper integral of 1 divided by x to the power of p, which you could check that it's on lesson 8, where I talked about this. We had a look at the values of p where this integral converges or diverges. Now let us consider the series that is given by this now. So for what values does p converge or make the series converge or diverge? So let us recall, so this integral from 1 to infinity, 1 divided by x to the power of p, converges whenever p is greater than 1, and it diverges otherwise. So therefore, for the series to converge, we need this to converge. We need the integral to converge, and which only happens when p is also greater than 1. And it also diverges when otherwise. So therefore, we could use the same result. It's the same result. So the p-series test and the integral test are very good related to each other. So these are some relationships that we could have a look at. So whenever we have a series that is where the p-value is larger than 1, we could already tell that the series will actually converge. All right, so let's have a look at the following theorem. So the P series converges if P is greater than 1, diverges if P is less than or equal to 1. Not too bad. All right, so let's have a look at a quick example. So let us circle the ones that the series converges by the P series test. Well, here, the first one, part A, this one will converge because the value of P here, which is 3, goes to here, therefore it converges. Part B and C do not converge. For B, we have 1/3, which is less than 1, therefore it diverges. For C, we know that's the harmonic series, so automatically that will also diverge. For D, ignoring the constant, we could move that outside technically, and we would have 1 divided by n to the 4. So since the 4 is larger than 1, it will actually converge. So D also converges here. Perfect. All right. So we had a look at, we'll have a look at this example now. So let us determine whether the series ln of n divided by n converges or diverges. So we're going to let f of x to be equal to ln of x divided by x. And this is for x from 1 to infinity. Then we compute the integral given by this. So that's ln of x divided by x. We can apply a substitution here. So we're going to let u to be ln of x. Then du is going to be 1 divided by x dx. And so when x is equal to 1, then u is equal to 0. And when x is equal to infinity, or approaches infinity, then u also approaches infinity as well. So therefore, we now have that the integral from 0 to infinity of u du, which if we compute this, we get half u squared between 0 to infinity, which turns out to be just infinity, therefore diverges. So the integral diverges. So that also means that by the theorem, it also diverges as well. So therefore, the series diverges as well. Perfect. All right, so let's have a look at one particular example, which you might see later on. So the Riemann zeta function is a way for us to find the exact values of a p-series, provided that it converges. So the Riemann zeta function is defined by zeta of x, where we have the series of 1 divided by n to the power x. So one known value of the Riemann zeta function is given by the following example. So this example, if x is equal to 2, then the exact value of the series is given by zeta of 2, which is equal to pi squared over 6. So that is exactly what we had to look at. So that means the sum of 1 divided by n squared, it's actually going to converge to pi squared over 6. Now with this, let us determine the values of each of these series over here, given that this series is equal to pi squared over 6. Okay, so for part A, if we want to find out what the sum of 1, starting from 2 this time, let us have a look at from 1 first. So we have that the infinite sum of 1 divided by n squared, that is also the same as saying 1 plus the infinite sum, n is equal to 2 to infinity, of 1 divided by n squared. But since the left-hand side is equal to pi squared over 6, 6 squared, and we have 1 plus the sum, starting from 2 to infinity, this is just going to equal to pi squared divided by 6 minus 1. So it's just a little bit of rearrangement here. So because this is the series that we want to be finding, so we just had to rearrange a little. Okay, so let's have a look at the next one. For part B, we have starting from 3 this time, and we also have n plus 1 in the bottom. However, let us rewrite this series a little. So we're starting with this. And since if we put 3 in, we get inside 4 squared. So that also means we could also write this as the infinite sum, n is equal to 4, 1 divided by n to the 4 cube, or n squared, sorry. Okay, so same thing as before. If we have a look at this series first. So now, from here, 1 divided by n squared, this is equal to 1 plus 1 divided by 2 squared plus 1 divided by 3 squared plus the series continuing on, starting from the fourth term. Since the left-hand side is equal to pi squared over 6, and the rest we have 1 plus a quarter plus a ninth plus the sum. And since we were trying to solve for this variable or this value, we could just rearrange so that we get, so that's 1 divided by n squared, starting at 4. This is pi squared divided by 6 minus 1 minus a quarter minus a ninth. So that is the value here. All right. And let's have a look at one more example. Let us find the value of 1 divided by 2n squared, or the sum of this. First, let us note that here we could rearrange or expand an exponent so that we could write this as 1 divided by 4n squared. So since 1/4 is just a constant, we could pull that out, and so that we just had the series 1 divided by n squared. Because this part over here is equal to pi squared over 6, the final result would just be pi squared divided by 24. So those are the 3 values that we could find using the Riemann zeta function given the value of this, which is pretty nice to know about. Okay. So let us have a look at the next section, which is called the comparison test. So remember when we talked about improper integrals, we had to look at integrals that are kind of hard to compute. So we had to use the comparison test for the integrals to determine whether the integral converges or diverges. The same problem here for the series as well. So let us recall the comparison test for series or integrals. So recall, suppose that f of x is larger than g of x and is larger than 0 for all x greater than or equal to a. Then 1, if this integral from a to infinity of f of x converges, then the integral from a to infinity gx dx converges. As well, if the integral from 0 or a to infinity of g of x diverges, then so does the integral from a to infinity of f of x. Okay, so first, let us consider this series that is given by the sum from 1 to infinity of 1 divided by 2 to the power n plus 1. So as we are able to relate integrals and series, we could also relate the comparison test between improper integrals and series. So this is known as the comparison test for series. So let us suppose that two series, so we have sum of an and the sum of bn, are series with positive terms. So this is important here. If the series bn converges and an is smaller than bn for all n, then the series or the sum an converges. Or alternatively, if an if the sum of an diverges and an is larger than bn for all n, then the sum of bn diverges. So that's the comparison test here. So now by using this theorem over here, let us assume that this series converges as well. We could use a larger series that is given by this one. So consider this one. Now, why are we considering this is because, well, for all n, if we have a look at the denominators, observe that 2n, 2 to the power n plus 1, is always going to be smaller than 1 divided by 2 to the power n, right? So as a side note, so we note that 2 to the power n plus 1 is always larger than 2 to the power n. So that means the reciprocal of this, 2n plus 1, is always smaller than 1 divided by 2 to the n, right? So therefore, by the comparison test up here, we have that this series converges. And so because this series converges as well. Because this is a geometric series. We know that geometric series converges whenever the common ratio is smaller than 1. Clearly, the common ratio here is smaller than 1. So that's why both of these series will actually converge. All right. So let us determine whether the following series will converge or diverge using the comparison test. So first of all, let us have a look at the series or the terms here first. Note that for all n, that 2 to the power n, or 2n squared, sorry, plus 4n plus 3 is always going to be larger than 2n squared. So that's the thing that we're going to be comparing to. So that means 5 divided by 2n squared plus 4n plus 3 is also smaller than 5 divided by 2n squared for all n. as well. So now by using the comparison test, since the series of 5 divided by n squared, 2n squared, converges, this is because of the p series, then that also means that this series also converges. Good. So this one we see that the series will converge. So let's have a look at the next one. So we had a look at this example before, the ln n divided by n. We know that the series diverges already by the integral test. But let us see what we could do by using the comparison test, see what we could compare it to. So we already know that this diverges. So note that for all n, we have that the ln of n is larger than 1, right? Because it's going to start from 0, and then it's going to keep on increasing from there. And so that also means, that ln of n divided by n is still going to be larger than 1 divided by n for all n. In particular, when we consider values for greater than 3, so not greater than or equal to the natural numbers. So because of this, because we have 1/3 here, we have ln of 3 divided by 3, and when it's 1, clearly this is not going to be larger than that. So there are some parts where it's not going to be larger. So this value is going to be larger than 1 divided by n for when n is larger than 3. So, and since this series here diverges because it's the harmonic series, that also means that the series of ln n divided by n also diverges. Great. So a similar comparison test can be used to determine whether a series converges or diverges. So the following theorem is called the limit comparison test. So suppose that the sum of an and the sum of bn are series with positive terms. If the limit of the ratio an divided by bn is equal to some number c, which has to be positive, then either both series converges or both series diverges. All right. So let us use this theorem to see whether this series over here will converge or diverge. So we're going to be comparing to another series. So let us say let an be the terms defined by this. As well, we're going to define another sequence by bn, which is given by 1 divided by 2 to the power n, just to make things a little bit easier here. Then, once we have, let us find the limit as n approaches infinity of an divided by bn. So that is equal to 1 divided by, the limit as n approaches infinity of 1 divided by 2n minus 1. This is multiplied by 2 to the power n divided by 1, so that's the limit as n approaches infinity of 2 to the power n divided by 2 to the power n minus 1. So I'm going to divide the numerator and the denominator by 2 to the power n, so that now we have the limit as n approaches infinity of 1 divided by 1 minus 1 divided by 2 to the power n. So as we send n to infinity, this entire thing is going to go to 0. So that means the limit here is equal to 1, which is greater than 0. So now by using the limit comparison test, it says that either both series converges or both series diverges. Since this series converges, this series would also converge. That would be the case. So that means the series converges since this series converges. All right, so let's have a look at another example that uses the limit comparison test. So let us determine whether the sum of 2n squared plus 3n divided by the square root of 5 plus n to the fifth converges or diverges. So we're going to let an to be the sum or the terms of the sum, and we're going to let bn to be the 2n squared divided by the root n to the fifth, or if you want, this is also the same as saying 2 to the power n 1/2. So now, then, we take the limit as n approaches infinity of an squared plus 3n. This is all divided by the root of 5 plus n cubed, or n to the fifth. Multiply that by the root n to the fifth divided by 2 n squared, which is actually the same as saying n to the half over 2. So I'm just taking the reciprocal of it and multiplying here. Now this is equal to 2 to the n 5 over 2 plus 3n to the power 3/2 divided by 2 times the root of 5 plus n to the fifth. Now if you compute this in limit, you should be able to get a value of 1, which is larger than 0. So since the series diverges because by the p series, then this series must diverge as well. Okay, so that is going to wrap things up for today's lesson. So the next lesson, we'll be having a look at some more series tests. In particular, we'll have a look at the alternating series test, and we will also have a look at the absolute convergence test. So if you have any questions, just feel free to let me know in the comments down below. And with that, I will see you guys in the next video.